In this module, we will now look at the radiation generated by compact stars and how we observe them, what do the observations tell us and what interpretation we can make of them. The generation of radiation from compact objects as we observe could be grossly divided into two parts. One is the self luminosity of the compact object, where the energy which is either trapped in the form of thermal energy into these objects being released slowly in the form of cooling, or processes in the magnetosphere which surrounds the compact object generating emission. So, either of these two we would classify under self luminous processes in the compact objects. And then there is also another big class of radiation mechanisms that get activated in compact objects when matter from either a companion star or the surroundings fall on the compact object and as a result get hot and start emitting radiation. The advantage of this accreting matter radiating while falling onto the compact object is that the matter itself, as it approaches the compact objects, gets very hot, and we see the radiation from this matter even though we are unable to see the radiation from the compact object itself in some cases. For example, if the compact object happens to be a black hole, the black hole is not self luminous. So, we do not see any radiation from the black hole itself, but the material which is approaching the black hole can be observed in the radiation that the accreting matter gives out, and as a result through this radiation the properties of the black hole can be probed. So, let us begin our discussion with self luminous processes. Let us start with white dwarfs. In a white dwarf, there is a significant amount of thermal energy which is trapped when the white dwarf is born. The white dwarf is born with a temperature in the interior anywhere between 10 million to 100 million Kelvin, maybe a little more. This is the temperature that the core would have had while the last stage of nuclear burning was going on. Now, when the white dwarf has formed, the object has become very compact. Heat from the interior will slowly leak out over time. This heat leaking out results in a certain amount of luminosity of the object, which is what we are able to detect. The degenerate interior of the star is in fact highly conducting, and it is almost nearly isothermal. The rate of escape of radiation from the degenerate interior is quite fast because of the high conductivity there. But the degenerate interior is not the entire white dwarf. The very outer parts of the white dwarf is in fact non-degenerate, and this non-degenerate envelope has a much higher opacity to radiation, and that is what eventually controls the photon escape rate. This kind of depth is what is appropriate for the envelope. This actually goes to fairly low density starting from 0. As you go to higher densities, that is deeper in the white dwarf, the matter is degenerate. But even though this is a very small outer skin, the opacity there is high and the net luminosity is controlled by this layer. So, in the envelope then the luminosity or the flux, which is luminosity by 4 pi r squared, can be related to the temperature gradient, which is proportional then to the opacity here is the mass density and this is the temperature. And combining this with the hydrostatic equilibrium equation for the envelope, dpdr g m rho by r squared, and the expression for the opacity itself, which is proportional to t to the power minus 3.5, one can then put it all together and find the relation between luminosity and the mass as shown here and the temperature. So, this shows you that the luminosity of the white dwarf is proportional to the mass of the white dwarf and temperature to the power of 3.5. So, from here if we actually see a luminosity of a white dwarf, we can infer what the interior temperature of the white dwarf is. The observed range of luminosities which we see, thermal luminosities from white dwarfs, are about 10 to the power minus 2, 10 to the power minus 3 times the luminosity of the sun, and that leads to a range of temperatures of the order of million to 10 million degrees Kelvin in the white dwarf interior. This is the present day temperature. The initial temperature when the white dwarf was born is slightly higher than this. Now, given that this is the rate of emission, rate of energy loss of thermal energy from the white dwarf, one can then compute how long the white dwarf will take to cool, and that one can easily estimate by taking the thermal energy content, which is proportional to the specific heat times the temperature times the mass, and divide it by the luminosity. Then you get a cooling time, which is given by this expression, and you can see once you put in the numbers, the cooling times can be very long, 10 to the power of 8, 10 to the power of 9 years. So, the white dwarfs, after they are born from the core of a star, they remain visible for a fairly long time, gradually cooling, but it is still available to observe for almost 10 to the power of 8, 10 to the power of 9 years. Similar effect also takes place in neutron stars. The neutron stars, when they are born, their interior temperature is even much higher. It is about 1 million electron volt, which means the temperature is of order of 10 to the power of 10 Kelvin. At such high temperatures, the cooling is dominated by neutrino emission processes. So, the neutrinos get generated in the interior because of various processes, both plasma neutrinos as well as what we normally call Urka process, where a neutron goes to proton and back to neutron. In the process generates neutrinos and antineutrinos. So, those neutrinos carry away a large part of the thermal energy when the interior is very, very hot. Once the interior temperature has dropped to below about 10 to the power of 9 Kelvin, then it is the cooling through the surface which becomes the main process of interior energy loss. And for an interior temperature of about 10 to the power of 9 Kelvin, the surface temperature of the neutron star turns out to be about 10 to the power of 7 Kelvin. The most of the temperature drop between the interior temperature to the surface happens in the neutron star crust, which is about 1 kilometer thick, as we discussed in the previous module. Based on the physics involved in this radiation transport, one can predict how the thermal luminosity of the neutron star, because of cooling, would behave as a function of time, and one can see that it starts high and then it gradually goes down, and there are a whole lot of curves here, and these correspond to predictions for different types of internal composition, and different types of envelope and atmosphere composition and so on. There are many uncertainties in this because we do not know the interior composition that well, and we do not know the interior state of matter that well, as we have already mentioned while discussing the equation of state of neutron star. The two figures below show the effect of magnetic field in the cooling. So, this is actually a temperature distribution on the surface as the cooling proceeds. The two pictures are for two different types of distribution of magnetic field in the interior. We discussed in the previous module that the interior magnetic field could either be permeating the whole interior, including the superfluid superconducting core, or the interior field could be primarily confined to the crust. Now, this picture on the left is the temperature distribution one would get if the magnetic field permeates the entire core, and the one on the right corresponds to the case where the magnetic field is confined mostly to the crust. So, if one is able to actually measure this temperature distribution on the surface of the neutron star, one will be able to diagnose the distribution of magnetic field in the interior. So, which is a very important observation here. Then there are other figures in these panels which show slight modifications of this cooling curves, as we call them, for different types of matter postulated in the interior. This is enhanced cooling, that is direct Urca process being involved. This is if the neutron star instead is really made up of a mixture of up, down and strange quark matter, which is strange star, and this is if the quarks form a color flavor locked phase, as we outlined in the previous modules. So, all of these give somewhat different cooling curves. So, in principle, if we measure with a population of neutron stars of different ages how the temperature is distributed as a function of age, then it may be possible to diagnose what the interior composition and the state of matter is in the neutron star. So, that was about thermal emission. The compact stars do not generate any thermal energy by themselves. There is no nuclear fusion process or anything analogous. So, therefore, the thermal energy is what has been trapped right in the beginning, and it just slowly leaks out. However, processes can occur in the magnetosphere of the compact object, which can lead to local generation of emission, and the energy that goes out in this emission comes at the cost of certain energy reservoir in the compact object, which we will discuss as we go along. Here is a plot which shows the magnetic field on the vertical axis and the spin period in the horizontal axis of a whole bunch of neutron stars which are engaged in magnetospheric emission. So, these black dots here are isolated pulsars, radio pulsars which produce radio emission. These red dots here and the red dots down there are pulsars which are radio pulsars, but as well as they produce a lot of gamma ray emission, and some of these gamma ray pulsars here are even not seen in radio as yet. These blue dots up there are what we call magnetas. So, these have extremely strong magnetic field, and it is thought that the emission, the magnetospheric emission that they produce, the energy reservoir they are trapping is the interior magnetic field of these neutron stars. So, we will come to these one by one. Starting with radio pulsars and some of the gamma ray pulsars which are rotation power. Here the radiation is generated in the magnetosphere surrounding the neutron star, but the energy reservoir that is being tapped is the spin of the neutron stars. The spin period of neutron stars, as you already know, could be very short. Neutron stars are known to spin very fast. The rotation powered pulsars have spin periods in the range about a millisecond to about a few seconds, and the range of surface magnetic field is somewhere between 10 to the power of 8 to about 10 to the power of 13 Gauss for these rotation powered pulsars. The main presence of these rotation powered pulsars are at radio wavelengths. So, about 2000 of them known in radio, but now more and more of these pulsars are also being found at high energy. So, currently this is well over 100 objects which have been seen at high energies, which is in X-rays and gamma rays. When a neutron star is spinning, if some part of the energy is lost in a process like the pulsar radiation or anything else, one would expect that the rotational energy is reduced and hence the pulsar spins down, and this can be measured. We can measure the spin of a pulsar, and we can measure the spin as a function of time, and from that we can see that almost all of these rotation powered pulsars that we are talking about are spinning down with time. So, given the fact that we measure a spin rate and the rate of change of that spin rate, which is spin down rate, and knowing the standard structure of a neutron star, its moment of inertia and so on, one can easily compute a quantity which is the rate of loss of spin energy, or E dot spin down. If you compare this with the luminosity of these stars in radio band, one finds that the luminosity of the radio band is always much less than the net spin down energy loss that the pulsars exhibit. The most of the radiative luminosity is actually emitted not in radio wavelengths, but at higher energies, X-rays and gamma rays. There is also another big difference between the radio emission process and the high energy emission process in these rotation powered pulsars. The radio emission happens to be a coherent emission, which means when you have a large number of electric charges participating in the radiation process, the individual particles, let us say individual electrons, if they emit a certain intensity and if you add the intensity emitted by all the individual electrons, then you get a total intensity. If that intensity happens to be the sum of the intensities emitted by each of these electrons, then we call that an incoherent addition of radiation. So, that is incoherent emission, and this is what high energy emission from pulsars look like. Whereas, in radio it is the emission process is such that it is as though large number of this emitting particles actually get together, and it is the combined charge of all these particles appears like a big charge, and this big charge coherently radiates instead of the intensity of individual particles summed together. Now, we have all the charges coherently acting together and producing an intensity which is like from a charge which is much larger than the original individual charges. So, for a given number of emitting particles, coherent emission is much brighter than the incoherent emission, and the radio emission process in fact falls in the class of the coherent emission. What is shown in the bottom here are records of pulses in radio wavelength from a certain pulsar. These pulses occur as the neutron star rotates, there are beams of emission which emanate from the magnetic poles. The magnetic axis in general is slanted with respect to the spin axis, and this beam of emission therefore rotates in space like a lighthouse, and when one of these beams of the lighthouse points towards an observer, points towards us, we see a peak of emission, and as the beam moves away the emission drops. And then in some cases, if you are suitably located with respect to this geometry, we may be able to see both beams, or we see one beam, or in some cases we may not see it at all. In that case, that pulsar will be invisible to us. These emission spikes tell us that these beams are very sharp, and the entire emission mechanism involves a very strong, very narrow angle beaming. This is only possible if electrons or positrons or any other charged particle which are involved in the radiation process, they are moving at extremely relativistic speeds, very close to the speed of light. When a charge moves at a very high speed, very close to the speed of light, then the emission pattern from that charge gets very strongly beamed in the forward direction within a cone angle of 1 over the Lorentz factor. So, the Lorentz factor has to be high for the emission beam to be confined to very narrow angles, and that is what we believe happens in pulsars. So, the magnetosphere of pulsars must be a region where charged particles can be accelerated to extremely high velocities, extremely high energies with high Lorentz factor. Now, a spinning magnet, if we do not even talk about any charges, just put it in a vacuum and spin a magnet, the magnet will generate a magnetic dipole radiation, and that magnetic dipole radiation can be computed to give a radiated power, which is this Larmor formula that gives you a radiated power proportional to the square of the magnetic field, 6th power of the radius, and in fact this b squared r 6 is nothing but the magnetic moment squared times omega to the power of 4, where omega is the angular frequency of spin, and sin squared alpha, where alpha is the angle between the magnetic axis and the spin axis. So, this must be equal to the rate of loss of rotational energy. So, rotational energy being half I omega squared, so rate of loss is I omega times rate of change of omega, which is I omega omega dot. So, once you take this and you can equate this, then this yields an equation where you find that b squared is proportional to spin period times rate of change of spin period. Remember, omega is just twice pi by p. So, write this in terms of p, and then you will find this relation between magnetic field and the spin period and the rate of change of spin period. So, since we can measure both these quantities of any pulsar, we can use that to yield a measurement of the surface magnetic field. So, measurement of spin down rate therefore helps estimating the magnetic field. The magnetic field in the units of 10 to the power of 12 Gauss is equal to square root of period of the star in seconds times rate of change of period in units of 10 to the power of minus 15 seconds per second. This is true for a moment of inertia, which is a neutron star moment of inertia, which is about 10 to the power of 45 gram centimeter square. From p and p dot, we can also roughly estimate the age of an object by just taking the period and dividing it by p dot, and we find that the range of ages that this rotation pulsars that we have observed lie anywhere between a few hundred years to several millions of years. So, but the younger ones with ages up to a few thousand years are often found inside supernova remnants, and that is not surprising because we have already mentioned that the formation process of a neutron star is accompanied by a supernova explosion. Now, this expression used just the vacuum dipole radiation to connect magnetic field and period and p dot. In reality, the spin down actually happens due to a large number of charged particles being accelerated, and those accelerated charged particles carrying away the rotational energy of the neutron star. But detailed computations have shown that the spin down due to particle wind gives a result which is very similar to this. So, we can continue to use these expressions for an approximate estimate of the neutron star magnetic field. So, if we take these observations and take p and p dot, and from that we compute the surface magnetic field, surface dipole magnetic field, and plot them against the spin period, then for radio pulsars we find a large majority of them located in this island, which has a median field of about 10 to the power of 12 Gauss. And then there are a bunch of pulsars which are spinning very fast and have lower magnetic field of the order of 10 to the power of 8 Gauss, and then there are a few pulsars in between. This set of pulsars are known as millisecond pulsars. They have had a certain complex evolutionary history ending up in this corner of the field period diagram. We will come to that process as we proceed further in our exposition of neutron stars. Now, we can see that these pulsars are all confined to the left of a line, a sloping line like this black line which I have shown here. Now, this black line actually is not a fit to this population, but it is an estimate based on theoretical computation of what combination of magnetic field and period is needed for a large number of charged particles to be generated by pair production in the magnetosphere of pulsars. So, if the field and period combination goes to the right of this line or below this line, then the voltage generated in the magnetosphere is too small to have a large amount of pair cascade. So, assuming that pair cascade is essential for generating this strong luminosity from the pulsar magnetosphere, one would say that if pair cascade does not occur well, then the pulsar should stop functioning. And by and large, the observed pulsars do show that trend. We have very few pulsars to the right of this line. So, nominally this line is therefore called the death line, and the region to the right of this line, right and below this line, is called the pulsar graveyard. So, as a pulsar begins its life, it could be spinning at a fairly short period with a strong magnetic field, and over time, as the radiation takes away energy from it, the pulsar will spin down. So, it will keep moving to the right on this diagram, and at some point it will cross this death line and it will stop functioning. So, that is the general evolutionary sequence that a pulsar will follow, and we will see how that evolution coupled with other effects can take a neutron star from this region through a whole lot of evolutionary processes down to this region in millisecond pulsar. So, that brings us to the question of how the pulsar radiation is actually generated and what are the processes that go on in the pulsar magnetosphere. Pulsar magnetosphere is actually an extremely active zone. And this is related to the fact that given the strong magnetic field of the order of teragauss and spins which could be of the order of seconds or faster, the voltage drop that such a spinning magnet can create is so high that all kinds of exotic processes will come into being. A simple estimate of the voltage that a rotating magnet can generate is obtained by just taking the magnetic field, multiplying it by the angular velocity and the radius squared. So, in this case we have a magnetic field of about 10 to the power of 12 Gauss, angular velocity let us say it is of the order of 1 and radius is 10 to the power of 6 centimeters or 10 kilometers. So, if we do this sum, then we will find that the voltage drop that is created in the magnetosphere at the stellar surface will be even higher than 10 to the power of 15 volts. So, 10 to the power of 15 volts is an enormous voltage, and with such a voltage charged particles can be pulled out from the surface unless there is some space charge to limit this voltage will rip out charged particles from the surface. Now, if we pull out some charged particles from the neutron star surface, that charged particle will then start moving in the magnetosphere, and because there is this extremely high voltage, this charged particle will be accelerated to extremely large energies. If for example, you had exposed one electron to 10 to the power of 15 volt potential drop, then at the end the electron would have acquired a 10 to the power of 15 electron volt of energy, and the rest energy of an electron is only about 511 kilo electron volt. This will lead to a Lorentz factor which is enormous, of the order of a billion or so. So, there is a very large amount of electric field available in the pulsar magnetosphere, which can easily accelerate particles to extremely high energies. Of course, this entire 10 to the power of 15 volts is not available for each charged particle to be subjected to, and that is because of the following processes. What happens is, once some charged particles could be pulled out and get accelerated in the pulsar magnetosphere, once they encounter this magnetic field, they will begin to radiate, and as they radiate, this radiation will happen at very high energy gamma rays. These gamma rays will interact among themselves as well as with the magnetic field to create electron positron pairs, and from each charged particle that you pull out, you have these stages of generation of radiation, then that radiation generating electron positron pairs, those electron positron pairs also getting accelerated in the local electric field and producing further radiation, and those producing further electron positron pairs with many levels of this cascade. You have a very large number of charges that are generated in the magnetosphere with the multiplicity is extremely high, maybe of the order of million to a billion for every charged particle you initially started with. So, now with all this charge available in the magnetosphere, the charges can now move to according to the local electric field to short out this electric field. Charges can preferentially move along the magnetic fields. The magnetic field being very strong, it is difficult for charges to move across the magnetic fields. The majority of the motion of the charges will be along the magnetic field. As the charges move along the magnetic field, they can redistribute themselves and create a situation where the electric field along the magnetic field is nearly 0, because even if there is a residual electric field present, the charges will redistribute themselves to short out that electric field. So, for most of the magnetosphere this is going to happen, and as you short out the electric field, the effective voltage that is available to a new particle coming in for being accelerated goes down. So, this entire 10 to the power 15 electron volt 15 volts is not available for a charged particle to be accelerated to, it will be significantly lower. But even then the Lorentz factors that get generated for these charged particles in the magnetosphere will be very, very high. The amount of charge density that you need to keep E dot B exactly equal to 0 is given by omega dot B, that is angular velocity dot product with the local magnetic field divided by 2 pi c. So, if at every point in the magnetosphere this kind of charge density can be generated and kept, then E dot B will be equal to 0 over the entire magnetosphere. Now, this is okay in the closer set of magnetic field lines, which is shown in the hatched region over here. These are magnetic fields which co-rotate with the star. Of course, the entire magnetic field is anchored to the star. So, you would expect all magnetic field lines to be co-rotating with the star. But since the star is spinning so fast that there is a distance beyond which co-rotation will mean moving with a circular velocity which exceeds the speed of light. So, this distance is called the speed of light cylinder or light cylinder. Now, there will be a whole lot of dipole magnetic fields which will close within this light cylinder, and they can happily continue to co-rotate with the star. But a few magnetic field lines closer to the magnetic pole will tend to close outside this light cylinder, and since closing outside the light cylinder and rotating with the neutron star would imply local circular speed at these points larger than the speed of light, this process is not possible. So, what happens is that these field lines become open. So, they go through the light cylinder and then proceed to infinity as open field lines. This open plasma on this open field lines cannot continue to co-rotate with the star because of this condition. So, in the region that is occupied by the open field lines, that region of the magnetosphere will not have this E dot B set exactly equal to 0, and there will be a residual electric field, and this residual electric field is going to act as the accelerator of the particles. And this accelerated particles are then responsible for the emission that is generated in the magnetosphere. So, let us take stock here. What happens is, because the star is rotating, the rotation creates a large amount of electric field in the magnetosphere. This electric field then accelerates particle and transfers some of the rotational energy of the neutron star to the kinetic energy of the particles which are being accelerated. These accelerated particles go through open field lines and escape to infinity. So, they take away the rotational energy of the star in the process, and as a result the star spins down. These particles, as they move through this magnetosphere, they undergo all kinds of radiation processes, create radio emission, high energy emission and so on, and we are able to observe this radiation and thereby observe the pulsar. And since the particles are very highly relativistic, the emission is directed in the forward direction along their velocity, and as they move primarily along the magnetic fields. The effective radiation is in fact beamed along the magnetic field lines, which are close to the magnetic pole, because it is only the open field lines where this occurs, and open field lines are restricted to a small region near the magnetic pole. And so therefore, this eventually becomes the reason why the radio emission from pulsars, for example, are like two cones of two beams of emission attached to the magnetic poles of the star. Now, to make a fully self consistent model of the magnetosphere, one needs to carry out a global magnetospheric solution. One of the ways of doing it is to create a plasma field solution which satisfies this force free condition, which means E dot B is equal to 0 everywhere, and the force free condition through Lorentz force is expressed in this manner. So, if one does that, then one finds that one needs a boundary condition where currents will need to be converted into return currents, and those regions will not have E dot B equal to 0, and it is in those regions you will have large amount of electric field left, and those will act as strong acceleration regions. And in this diagram you can see a couple of regions. One is this gray region, which is the co-rotating magnetosphere, and then this upper region and lower region, which are open field line regions, and then there is a boundary between these regions, which is called the separatrix, and it is the separatrix where most of this return current is located, and this return current, and so in this current sheet one does not have E dot B equal to 0, and this region acts as a large particle accelerator. And these are some numerical simulations of this process where one can see that what is shown here are the electron density and the positron density, and the regions, as I showed you the current sheets, are the regions which harbor large amount of particle density. Now, coming to radiation processes, the radiation processes that are relevant for pulsar magnetospheres are: number one, synchrotron radiation. You release a charged particle in a magnetic field, the charged particle will gyrate around the magnetic field and produce synchrotron radiation. The synchrotron radiation for large Lorentz factors can come at fairly high energies. The peak emission for synchrotron radiation is 0.8 times Lorentz factor square megahertz for a magnetic field of 1 Gauss. So, if you have magnetic fields of 10 to the power of 12 Gauss, then you can see that it is actually very large energy. What happens when these charged particles are released into the magnetosphere? They first do this synchrotron radiation, radiating extremely high energy gamma rays. The radiation comes at the cost of the electron momentum, which is perpendicular to the magnetic field. Very soon that energy is completely radiated away, and the electron is not left with any energy perpendicular to the magnetic field, and it just keeps following the magnetic field. Once it does that, synchrotron radiation stops, but in the transition from the beginning to that state, it would have produced some very high energy gamma rays. Now, these high energy gamma rays then go ahead and do the pair production in the pulsar magnetosphere. So, these fast particles can also do Compton scattering. So, if you have one photon which encounters one of these fast moving particles, and they can the interaction can, through Compton scattering, boost the photon energy to a very large value. So, if the photon energy is h cross omega, then the relation between the photon energy, the initial photon energy and the scattered photon energy as follows. So, first we do a Lorentz transformation to the rest frame of the scattering particle. So, in that rest frame the photon energy now looks like omega prime, and in that rest frame the scattered photon energy is also roughly omega prime, but then when we transform back to the laboratory frame, that omega prime transforms to omega double prime, and this ratio roughly is 1 is to Lorentz factor of the particle times the Lorentz factor square. So, the omega double prime is roughly Lorentz factor square times the initial energy. So, a large amount of energy gain can happen due to Compton scattering by these particles if they interact with some of these highly accelerated charged particles which are present in the pulsar magnetosphere. And that way again very high energy photons are generated, which can then do further pair production. Now, I said that the charged particles themselves, as they completely deplete their momentum perpendicular to the magnetic field, they will now tend to move along the magnetic field. The magnetic field lines in the pulsar magnetosphere are not straight. Even if the shape of the field is pure dipole, the dipole fields have a certain curvature. So, through this process the charged particles will move along these curved field lines. Now, moving along curved field lines means that there is an acceleration because the trajectory is curved, and this curved trajectory, the acceleration due to it will then excite the charged particle to radiate, and the radiation by a charged particle is proportional to the square of the acceleration. So, the centripetal acceleration that is needed for the charged particle to move on a curved trajectory will lead to radiation, the properties of which are very similar to synchrotron radiation, except instead of the gyration radius around the field line, now it is the radius of curvature of the field line itself which replaces the gyration radius. So, this kind of emission has been given the name curvature radiation, and this curvature radiation produces most of the radio emission from pulsars that we see. The polarization of this curvature radiation is parallel to the projected field lines, whereas the synchrotron polarization is perpendicular to the projected field lines. And since the radius of curvature of the field lines are much larger than the radius of curvature of the particle trajectory when it was doing synchrotron radiation, the frequency at which the radiation comes out is much lower. So, instead of very high energy gamma rays being produced by synchrotron radiation, this slow curvature of the magnetic field line actually produces radio emission. The radio emission from pulsars have some specific characteristics. As I already mentioned, the pulses tend to be very sharp, but the radiation also tends to be very highly polarized, and if we look at the position angle of the polarization, it undergoes a characteristic S-shaped sweep through the pulse, and this is understood as the fact that as our line of sight cuts through the emission cone, we are looking at projections of the local magnetic field, and this projection of the local magnetic field changes in direction as our line of sight cuts through the beam, as shown in this diagram. So, first we encounter a field line like this, where the polarization vector will be parallel to this, then the polarization vector will be parallel to that, then to that, then to this, and so on, all the way to this, which will then explain why we see an S curve of this kind. This is called a rotating vector model, and using this various aspects of pulsar emission cone geometry can be measured. The phenomenology also contains stochastic variation of intensity from pulse to pulse. Every pulse that we see from a pulsar does not look the same, whereas if we average over many pulses, then the average is sort of stable. So, if I take 1000 pulses on average and I take next 1000 pulses on average, the shape of the pulse will be very characteristic of a given pulsar, and that shape will be constant, which from one average to another average. But for individual pulses, as is shown here, a train of pulses, they can look quite different. So, it tells us that the emission phenomenon is somewhat stochastic, but there is a overall geometric envelope within which it occurs. There is also another phenomenon which can be seen in this diagram, that from one pulse to the next, the emission longitude is shifting slightly in a very orderly fashion. So, you see these diagonal lines, diagonal sloping lines which are here, this type of diagonal lines. And so this is thought to be caused by the sparks which give rise to this particle injection rotating within the pulsar beam due to the well known electric field called cross magnetic field drift of plasma. Radio pulses, once they are emitted from the pulsar, they traverse a long distance through the interstellar medium to reach us. So, this propagation through the interstellar medium changes certain attributes of the radiation that we receive, and measurement of that one can use to good effect. One important effect is dispersion. The phase velocity of radiation through the interstellar plasma has a dispersion relation of this kind, where omega p is the plasma frequency. So, this tells us that the speed of propagation is not the same at all frequencies. So, if we take a typical pulsar and take different radio frequencies and look at the arrival time of that pulse, we see a slope across the observing band. So, we can measure this dispersion through the band, and that dispersion then is related to this omega p. Omega p is related to the plasma number density, and the net effect is integrating this over the line of sight from the pulsar to us. And so, this dispersion measure gives us a measure of the number density of electrons in the line of sight integrated over the line of sight from us to the pulsar. Now, with independent knowledge of the average electron density in the line of sight, this in fact can yield an estimate of the distance to the pulsar, and this is often used as a distance indicator to the pulsar. Another effect that the plasma causes is Faraday rotation, because the interstellar plasma also has embedded magnetic field, and similar to dispersion measure, we can also measure this rotation measure by how much the polarization is rotated due to the propagation, and that gives us an estimate of the average magnetic field in the interstellar medium in the propagation region. Further effect includes scattering, and due to scattering of radiation from the irregularities in plasma distribution in the line of sight, the pulses can often get broadened. A sharp pulse can be broadened into this characteristic fast rise and exponential decay kind of profile, and from that we can measure the inhomogeneity distribution of plasma in the line of sight. Coming now to high energy emission. The high energy emission is not due to curvature radiation in general. It is more likely that they are from synchrotron emission or inverse Compton emission in regions which are somewhat far away from the surface of the star. if one looks at the distribution of Lorentz factors of accelerated particles, then one can see that the current sheet that I was talking about is the region where the particles acceleration is most active, and most of the high energy particles are located in there. And one can now compute all the radiation processes that this particle will go through, including curvature radiation, synchrotron radiation, inverse Compton and so on, and that will then give us an idea of what kind of high energy emission can be produced. This is an estimate of the photon density created by those charged particles, and as one can see that mostly this separatrix and the current sheet are the regions where most of the radiation is getting generated. And because of this kind of geometry, when if you project the emission pattern into the sky, it usually is a double humped pattern. And this is an example of the emission pattern that we see at high energies. This is one of the well known pulsars called the Crab pulsar. We have in radio a sharp main pulse and a small interpulse which likely occurs from the other pole. And in case of high energy emission, the pulse profile is quite different. One does not have two humps, one does have two humps, but there is a large bridge of emission which connects the two humps. So, clearly the emission region from which this two bands originate, this is radio on top and X-ray below, those emission regions are different, and this observation is consistent with the fact that the radio emission might be coming from narrower cones near the surface, while the high energy emission is coming from the current sheet which is on the separatrix and beyond the light cylinder. So, the Crab nebula is the supernova remnant which harbors that pulsar that I showed in the previous slide. The center of this supernova remnant contains a neutron star which is seen as the pulsar. This is a famous historical supernova recorded in the year 1054 AD by the Chinese, and it at the location of the supernova that occurred at that time, now there is this supernova remnant that can be seen. In addition to the expelled hot gas which is seen in these filaments, you also see a diffuse glow which covers the interior of the supernova remnant, and that diffuse glow is caused by these charged particles, accelerated charged particles that the pulsar generates, which then escape from the pulsar through open field lines and then populate the interior of the supernova remnant. So, the continuum emission spectrum of the supernova remnant and the pulsar show that there are relativistic charged particles which have been produced, and both the pulsar itself, which is this grayish set of points, and the nebula, they both derive their energy from these charged particles which are accelerated by the pulsar. I also mentioned a class of objects called magnetars. These are objects which have extremely strong magnetic field, above 10 to the power of 13, going all the way up to few times 10 to the power of 15 Gauss. Their emission process is somewhat different from the radio pulsar emission process we discussed. The magnetars, all of them show outburst. There are some class of magnetars called soft gamma repeaters, which show more violent outbursts than another class of magnetars called anomalous X-ray pulsars, but both do show outbursts. And after the outburst, there is a cooling quasi-thermal radiation which can be seen at X-ray wavelengths. And there is a power law tail to this emission going to pretty hard X-rays, as well as a strong hard X-ray emission above 10 keV, peaking at about 100 kilo electron volts. So, this type of spectrum is very different from the radio pulsar spectrum that we see, and also the emission mechanism is different. So, what is believed is that these magnetars have a strong internal magnetic field which causes crust quake from time to time and releases some of the magnetic free energy. And this crust quake then shakes up the magnetosphere very violently, and this change in external magnetosphere causes a twist, and that twist generates currents, and these currents then generate large number of charged particles, and dissipation of these currents then generate the magnetar emission we see.